we saw that every problem can be translated into a satisfiability problems. But once you have a power of solving satisfiability problems, you can solve many other problems that may appear to be different from satisfiability problem, but that can be translated into satisfiability. Let's look at a few of those. Okay. So a typical logical problem can come in several forms. For example, it can come in the form, example of the question of validity. It can come in the form of implication. It may also come from a quantifier elimination, which will become clear in few slides. Sometimes satisfiability cannot be solved as the problem comes along. You need to use the induction method, and we will also show you what the induction method is. In this course, we will also cover these 3 more problems, but in this introduction, we will not going to go over them. Okay, let's look at these 4 problems. Let's look at the validity problem first. So what is a validity problem? Basically, if I give you a formula and you want to check whether the formula is valid or not. I have already hinted in previous sections is that we can easily translate this problem into a SAT problem, and therefore it's as hard as a SAT problem. So let me what you can do is you can simply check satisfiability of not of f, and if this formula is unsat, that implies f is valid. Otherwise SAT means not valid. For example, if you want to check the validity of this formula, which you have seen in the past, what you do, take its negative, which looks like this now. All the strict inequality becomes non-strict, and disjunction becomes conjunction. And now you can check the unsatisfiability of this formula. Now let's see what else we can do using satisfiability solver. Let's say you can check implication. We can check f implies g. What we want, in fact, when somebody asks you this question, is that we want to ask if this formula is valid or not. We have seen the trick in the past. Again, what we do is we basically check the unsatisfiability of the negation of the formula. And if it is unsat, then the validity of the implication. Consider this implication. This formula and implies this formula. To check the validity of this implication, what do? You negate this whole thing and simplify the formula. If we do that, what happens is we find conjunction of these 3 atoms. What we can do is we can first remove y from this equation. What we can do, simply write y equals to x minus 1. If you put it everywhere, you will find that, and simplify, you find these 2 atoms left. Okay, this thing will disappear. And once these 2 left, you can see that it wants that these 2 conjuncts are mutually unsatisfiable, because x minus z is greater than or equal to 4, and which cannot be the case because it also wants x minus z less than or equal to 0. Therefore, the negation is unsatisfiable and the implication is valid. Now let's look at another problem, which may not be that intuitive, which is called quantifier elimination. So let's suppose somebody gives you a formula f, and which has 2 variables, x and y, and it asks you the question that find me a g formula over y such that it is equivalent to there exists an x, f of xy. And this is a very important problem, and it occurs in many contexts. We will see in which context. But is it a harder problem than satisfiability problem? Yes, it is far more harder, and it is considered to be undecidable in generality. To really get an intuition, let's suppose you have 2 variables, x and y. So let's suppose this is x dimension and y dimension. This formula represents this triangle. Okay. So what is the quantifier elimination? Quantifier elimination is saying get rid of the variable x. It means is you projecting f on dimension y, and the projection is this segment, which is basically represents the g. So let me give you an example of quantifier elimination. Let's suppose I give you this formula in which you have there exists an x is greater than 0, and x prime is equals to x plus 1. Then what do? What we can do is simply apply substitution. basically wherever x occurs, we write x prime minus 1 and we obtain this formula, right? And if we obtain such a formula, there is no x occurring in this formula anymore. So what you can do, we can simply drop the quantifier and we obtain x prime greater than equal to 1. So let's suppose you have a property to prove, okay? And the property is that you want to show that this formula f holds true for all n. If you want to do that, what do? Well, you try to apply several techniques, but there is a very common technique you must have seen in your high school, that is called induction. What do? You first prove that f is true for 0, and then what do? You show that for all n, if I have fn, then I can prove fn plus 1. Okay, if you can show that this formula is valid and this also is a valid formula, okay, then you can demonstrate that this formula, this holds true. So this problem can be simplified into this problem. You may, if you have not seen any example, you may wonder why doing these two tasks is easier than doing this task, but once you see an example, it becomes very easy why that is the case. The problem is that whenever this kind of problem is offered to you, very difficult to automate. Induction, like machines find it very difficult to automatically do inductions, and that's one of the Achilles heel in doing automated reasoning. Why that is the case? Okay, because we need to prove, let's suppose for is equal to gn, but the induction proof fails on g. Then we need to find fn such that fn implies gn and the induction works on fn. Okay, so the problem given to you is some other form. You need to translate the problem into an fn form such that you can apply the induction. Okay, so problem will not come in a very in a boilerplate form, then hey, oh, go do this induction for me. It will come in some other formula which you cannot really do induction on it, but if you somehow you have a very easy way to proving this, and then you can go on proving this guy and this guy, then you have a induction proof. Let's look at an example. Let's suppose we have a formula fn equals to summation of 0 to n numbers is n times n plus 1 divided by 2. We know this identity, but how can we prove it using induction? Okay. So first you put n equals to 0 and you check this formula is valid or not. So basically you can feed into a satisfiability solver and you can basically check it's satisfiable or not. Now you want to check that we can show that this implication holds. So how do you do that? You construct this implication, and you have this formula which is basically fn, and this formula which is fn plus 1. Okay, now what you can do is you can pass on this formula to a satisfiability solver, and it is a satisfiability solver would be able to check that this formula is a valid formula. So why that a satisfiability solver will be able to do that? Okay, so see how a satisfiability solver will going to prove its validity. So what it will do is it will break down this summation into two parts. It will say, okay, sum of I equals to 0 to n I, and then it says plus n plus 1, okay, equals to n plus 1 times n plus 2. Now this sum also same sum, I equals to n times n plus 1 divided by 2 is here. So this term is same as this term, right? So what it can do is substitute this value here, right? So what it will do is simplify the problem into n plus 1 divided by 2 plus n plus 1 equals to n plus 1 n plus 2 divided by 2. Now this you can apply a arithmetic reasoning and you can easily see this equality holds. But this arithmetic reasoning could not have been immediately applied to this formula. You wouldn't know how to go about applying arithmetic reasoning because you have an unbounded sum written here, which you do not know how to handle in simple arithmetic operations. But just by using induction step, you broke down your unbounded sum into two parts like here, and you managed to get around this problem of handling unbounded sums. That's the key reason the induction added in your arsenal more proof technique. This ends the discussion on the derived problems from the satisfiability problem. If you have a satisfiability solver, using those solvers, what else you can do? And in the next lecture we will look at the formal definition of logics